Hi, I'm Callum Lorimer. I've been working in the Neuromechanical Intelligence Lab at WVU this summer with Dr. S, and this is my project, a PID controller for efficient position and stiffness control of a bio-inspired actuator. Current legged robots struggle to maintain their posture and perform coordinated movements in an energy-efficient manner. Significant factors limiting legged robot energy efficiency include shock absorption, energy storage and release, as well as high torque required from motors while walking or maintaining posture. In animals, energy-efficient locomotion and posture control is achieved through coordination of slow, intermediate, and fast muscle fibers with distinct neural and mechanical properties. Slow muscle fibers constantly work in the background to passively adjust the stiffness and position of joints, while intermediate and fast muscle fibers are activated during large-scale movements where more force is required. The goal of our project is to use bio-inspired techniques to build and control a robotic actuator capable of maintaining a constant position against external forces indefinitely while consuming no energy, as well as following a sinusoidal reference position while consuming extremely little energy by using slow muscle fibers to set the natural frequency of the joint to match the frequency of the reference position. We've created a model actuator based on the anatomy of Drosophila and MuJoCo physics simulation. The joint has elastic elements representing muscle fibers on each side. These are the slow flexion and slow extension muscle fibers. Like Drosophila, these muscle fibers exert a nonlinear amount of force as they are stretched from their initial length, which allows us to modulate the stiffness and natural frequency of the joint depending on the degree of co-contraction. The length of slow muscle fibers is controlled by non-backdriveable actuators, which like slow muscle fibers are highly efficient in holding their position and compensating for external forces but are much slower and less responsive than the backdriveable actuators that we're using to model intermediate and fast muscle fibers. When these motors are working in parallel, it allows for efficient stiffness modulation and force compensation while also achieving high responsiveness and torque output. To control the three actuators present in the model, we are using a modified PID controller. The slow muscle fiber lengths are a function of the desired stiffness and natural frequency of the joint, while the input to the non-backdriveable actuator is a sum of the proportional, integral, and derivative error functions, as well as a feed-forward force based on the desired position of the joint at any given point in time. This controller can be tuned to allow for extremely accurate position tracking over a wide range of frequencies and amplitudes. When tracking a sinusoidal reference position, the actuator tunes the natural frequency to match the frequency of the movement, allowing us to save significant amounts of energy across a range of input frequencies when compared to an actuator with no elastic elements carrying out an identical movement. Accurately producing these sinusoidal movement patterns with low energy cost will facilitate more efficient walking and legged robots. When given a static positional input and an external torque is continuously applied to the joint, the slow muscle fibers adapt to compensate for the external torque while holding the desired resting position at no energy cost after the joint reaches equilibrium. This allows legged robots to hold their postural positions, compensate for external forces, and absorb sudden impacts passively, vastly increasing energy efficiency and robustness. This model will be used as the basis for producing a physical prototype. Integration of this actuator with legged robots, such as our lab's Drosophila, a hexapod robot replicating Drosophila anatomy, will facilitate gains in legged robot adaptability, robustness, and energy efficiency. This will increase applications in complex terrains in industry. This work was supported by the NSF-RU for robotics research in rural Appalachia. I'd like to thank the program directors as well as the members of the Neuromint Lab for making this such a great experience. Thank you.